Hello. In this and the next video, we are going to discuss the synthesis of an important class of organic compounds, the nitriles. The compound hydrogen cyanide, also called hydrocyanic acid, features this carbon-nitrogen triple bond. The nitriles can be thought of as a modification of this structure where we add an organic group in place of the hydrogen attached to the carbon of the carbon-nitrogen triple bond. If we formally replace the hydrogen of hydrogen cyanide with a methyl group, we get the simplest of the nitriles. The IUPAC name for this compound is ethane nitrile. Ethane because it has two carbons, and we call two carbon species with the eth prefix. It is most commonly known as acetonitrile, where we name it as if it were a derivative of acetic acid, which is the 2-carbon carboxylic acid. It is also sometimes referred to as methyl cyanide. So an important difficulty of the nitriles is that a number of mutually exclusive and contradictory systems of nomenclature are used almost interchangeably among scientists. The next nitrile in the series is propionitrile, also sometimes called propionitrile, and ethyl cyanide. The next nitrile in the sequence, and the last nitrile that we are going to discuss in this video, has this particular structure, which has the IUPAC name of butanenitrile. Because the corresponding carboxylic acid is butyric acid, this can be called butyronitrile. The last possible name for it is 1-propyl-nitrile. Also note that these can be named as cyano derivatives. So for example, we can call this particular compound up here, because of the cyano group, cyanomethane. The compound below it is cyanoethane. And then here we have 1-cyanopropane. Please see the following figures which show computed structures for these compounds. CH₃CN, hydrogen cyanide, is a weak acid, which means that its conjugate base, cyanide ion, is a relatively strong base. Because it is a relatively strong base, it is an effective nucleophile. So we can imagine forming a nitrile by nucleophilic attack of cyanide ion on, for example, a haloalkane, since we know that the halogens in particular are mostly good leaving groups. A couple things to talk about first is that the cyanide ion is somewhat peculiar in that even though there's a bond between carbon and nitrogen is a more electronegative element than carbon is, the negative charge of the ion actually resides preferentially on the carbon end of the molecule, which is surprising. So therefore, the actual nucleophilic attack takes place from the carbon end and not from the nitrogen end. You'll notice in the figures in the video that the cyanide ion is always presented in this direction to show it coming from the left, and with the carbon being the actual nucleophilic end of the species. Cyanide attacks the molecule in an SN2 fashion, so recall that we have a heterolytic bond cleavage of the leaving group, which takes an electron with it, a pair of electrons, so it ends up having a negative charge. And then we have attack of the nucleophile on the electron deficient carbon. And these encounters happen at the same time, so we end up with a 5-coordinate transition state. The result of the reaction is the formation of the nitrile and the leaving group leaving with a negative charge. In this video, we are going to exploit two features of electronic structure calculations that you may not have seen before. In one case, we are going to look at the case for several different examples where the leaving group is also cyanide ion. So we have cyanide as the nucleophile and the leaving group X at the same time. In reality, we know that in actual laboratory practice, this would not yield a successful reaction because for the reasons that make cyanide such a good nucleophile, its strong basicity, is precisely the reason why it would be a very poor leaving group. But electronic structure calculations allow us to examine a what-if situation. And the nice thing about that is it gives us a reference point for the reaction where the nucleophile and the leaving group are exactly the same species. And this is particularly valuable in that we can see that in those cases that we have a very clear symmetry of the transition state. You'll see that the distance from the nucleophile to the reactive carbon is exactly the same as the distance between the carbon and the leaving group. And this is only true when the nucleophile and the leaving group are identical to each other. The second case is we're going to look at, as far as other leaving groups, we're going to look at fluorine, chlorine, and bromine. And again, we realize that fluorine in general is a very poor leaving group because it's a relatively strong base. But we can examine and calculate what the energy of activation would be for the transition state should we be able to get that reaction to take place. And we will notice that our expectation is that the energy of activation for fluorine should be much higher than for chlorine and bromine as leaving groups, which we know are much better leaving groups. And this will be confirmed. So we will note that a huge advantage of electronic structure calculations is that we can predict what-if things that we could never achieve in the real world because side reactions might take place or they might be just way too dangerous. But they do provide a very convenient reference point. So in our actual case here, our generic mechanism, we'll see that we have, in every case when we show the diagrams, the nucleophile will be coming in from the left and the bond that is starting to form will always be dashed. And then we'll see that the leaving group is to the right and that the bond that is breaking will also be dashed. The first set of reactions we are going to look at in detail is the SN2 reaction of cyanide attacking halomethanes. And the halomethanes that we're going to look at are fluoromethane, chloromethane, bromomethane, and then the equivalent nucleophile and leaving group where they have the cyanomethane, which would also be called acetonitrile. So here we see, even though this is not going to be generally practical in the laboratory to have fluoride as a leaving group, we see the formal structure of the reaction, and we'll see in the following figures the computed structures for the reactants, the products, and the transition states for the various types of SN2 reactions. One thing to note in the following table is that the energies of activation are lowest for bromine as the leaving group, which is exactly what we'd expect because bromine is the best leaving group. We'll see that the worst leaving group are going to be either the fluorine or the cyano, depending upon the case, which is exactly what we'd expect because we know that those are very poor leaving groups. And we would see that the value for chlorine is somewhere in between, which is what we'd expect because we know chlorine is going to be a good leaving group, but not quite as good leaving group as bromine is. In the next group of reactions, we're looking at the SN2 nucleophilic attack of cyanide on substituted ethanes. In this particular case, we have chloroethane. And we note that our product, as we'd expect, is going to be propane-nitrile, or propionitrile, depending upon how you want to name this compound, and chloride ion as the leaving group. Please see the following structures of the reactants, products, and transition states, and see the following table listing the energies of activation and the enthalpies of overall reaction for the 4 different SN2 reactions. Again, noting that the values for the energy of activation, which is the value we're looking at for how quickly the reaction takes place, is smallest when we have the bromide leaving group, and chlorine is the next best, and that the values for fluoride and for cyanide, the 2 poor leaving groups, are the largest. For the final series of reactions in this video, we're going to look at the nucleophilic attack of cyanide on 1 substituted propanes. So for example, here we have 1 bromopropane, and as we'd expect, the product of the reaction is going to be the butane-nitrile here, or butyronitrile, and bromide as the leaving group. So our major organic product is the nitrile. And this is by far the most effective way to synthesize nitriles in the laboratory. So please see the following computed structures of the reactants, the products, the transition states, and then see the table which lists the values, particularly for the energies of activation, which change depending upon the identity of the leaving group. And realize that the smaller the energy of activation, the quicker the reaction takes place, the more favorable it is, the more quickly it takes place, the more effective the leaving group is. You also see, for comparison, the overall enthalpies of reaction for those particular cases. Because this is an SN2 reaction, we see, and this is borne out by the results of the calculation, that it takes place most readily with the smallest energy of activation in the case where we have a methyl haloalkane, and that it slows down when we have a primary case. In the case of cyano substituents, when we have cyanide as our nucleophile, it is a sufficiently strong base that SN2 reaction will not take place even for a secondary substituted substrate because of the readiness with which elimination takes place. With a tertiary, you have no chance at all, but in this case, SN2 does not take place virtually at all for a secondary substrate because of the readiness with which elimination takes place. So in this video, we've concentrated on just the methyl and the primary case, and you can see that there, if you compare the energies of activation for the same leaving group, that the energies of activation are always smaller in the case for the methyl substrate, where we have less steric hindrance, than we do in the case of the primary substrates. So please see the following table, which shows these ideas numerically. I thank you once again for your kind attention. As always, have a good one.